divided up the string, the input string, into a region X, that bunch of symbols, like a substring, right? X, Y, and Z. And the Y, that was the substring that took the machine M from state Q9 to Q9, right? So the substring of the symbols in your input string, that we labelled Y. And the ones before that we labelled X, and the ones after that we labelled Z. Okay, now we're up to where we were at the end of the previous session, previous board. Okay, so we're splitting up the input string now into three substrings, X, Y, and Z. And so we have to show now that this string with these three substrings, three regions, satisfies the three conditions of the pumping lemma. Okay, that's what we have to show. Right? So now let's input this string, slightly modified. We now pump it a little bit. So we take this substring Y, make a copy of it, and insert it here. So now we've got X, Y, Y, Z. Okay, so we've pumped it a little. It's now a little bit longer than this one. Now, so we now input this pumped, slightly pumped. We only have one extra copy, okay, of Y in the input string, and we input this into the machine M. Well, what's it going to do? Well, the X part will take the machine. If you look at its sequence of states, it'll take M starting from Q1 to Q9. So the next symbol that it will read, the next input symbol that it will read will belong to Y. Right? It'll be the first symbol of Y. So the first Y will take you from Q9 to Q9. Right? Because that's what it did here. But now you've got another Y, so it just goes through the whole thing again. Right? It goes through the same sequence of states corresponding to Y. Okay, so you're back to Y again, and so now you're at the last symbol of Y, and then you read the symbols in Z, and you'll end up in Q13 again. I hope you follow that logic, because it's sort of the heart of the proof. If not, rewind. Okay, so can you see? If you pump this string a little, so you now have two copies of Y here, then as this string goes in, so the sequence of states of the machine M will, it'll go from Q1 to Q9, and then Q9 to Q9 for the first Y, and then again Q9 to Q9 for the second Y, and then from Q9 to Q13. So in other words, this is accepted. Okay? In other words, this string belongs to the language. Right? That was condition 1 of your pumping lemma. Now, can you see? Okay, now let it be Y, Y, Y. Let's have like 3 copies of Y. Now, can you see? Each Y will take the sequence of states in the machine from Q9 to Q9. And if we have 3 Ys, it'll just do this 3 times. And if we have it I times, if we pump here with I times, we'll just go from Q9 to Q9 like I times, right? So you probably see where this is going now, all right? So it doesn't for any I, positive I, integer of course, this will be accepted by the machine, and therefore this string belongs to the language A. Right? Now, if I is 0, this just becomes the empty string. So you're just left with xz, and that will be accepted, right? Because then the y drops out. So then you just the sequence of so if there's nothing between your Q9 and Q9, then it'll still it'll still end. It'll go through to Z and finish in Q13. I've put here question mark. Do that as homework. Convince yourself that that's true. So even if there's no Y here, this will still be accepted. So persuade yourself that find your own reasoning to show that that's true. All right. So condition 1 is satisfied, and what was that? That this string here for I non-negative, so in other words greater or equal to 0, integers of course. Okay. So this is recognized by the machine. It's accepted. In other words, this string for all non-negative I belongs to the language. Okay, so that's condition 1 is satisfied. All right. Now, okay. So now we need to show that where this also satisfies the other two conditions of the pumping lemma. All right. Now, so concerning condition 2, so we have to show that this satisfies condition 2 and condition 3, the three conditions of a pumping lemma. Now, so AKA, also known as, so instead of writing this long word concerning, about, when discussing ... so usually pretty common in English is just to use the very short word re, re. So concerning, also known as re. So re condition 2 or concerning condition 2. Why is the size of y positive? Right? Why is it positive? Well, because that y is the part of the string, the substring, that occurred between the two different occurrences of Q9. Okay. I'm a little puzzled here because y can be 0, and here it's saying it's not. Well, there's a I find this a lot in Sipser. Lots of little details that just leave me puzzled. Like, do you see what I'm talking about? Now here you're saying y, the size of y, the size of the substring is positive, so it can't be negative. But here you're saying I can be 0, so your y effectively is just an empty string. It seems to me it's contradictory. Well, this is something to think about. Right. Okay. So now re condition 3. So concerning condition 3. So ensure that make Q9. Let that be your first repetition in your n+1. The length, the number of states in the sequence of states as your machine M reads the input symbols of the input string one by one. So let Q be your first repetition. Okay, and then use the pigeonhole principle. Remember that. Well, just quickly. You have let's say M pigeons, and you have some pigeonholes, but less than M. You have less holes than you have pigeons. Now you put all the pigeons in the holes, the pigeonholes. So common sense says there must be at least one hole that has more than one pigeon, because there's just not enough holes for all the pigeons to be put in the holes. So there's only one pigeon per hole. Can't be done. There's too many pigeons, not enough holes. So that's the idea of the pigeonhole principle. Okay. Now let's see where this comes from. Still a little confused on the P and the N. Little n is the number of that's the length of your input string, and we let I'm forgetting one critical concept. It's not coming to me quickly. So what I do remember is that we deduced that there must be a repetition. There must be at least one state that's repeated, because the length of the sequence of states was n plus 1, and there are only n, and hence p. I think we chose as p the pumping number, as it's called, to be equal to the number of states. Okay, and so if we let n equals p, I'm thinking real time here, if you let n equal p, so let p be the number of states, so let the length of your input string also be p, and therefore the length or the number of states in the sequence of states as you read through that string of length little n, that will be n plus 1. Little n is by definition the length of your input string, so it's little n. But little n is p. So now the length of your the sequence of states the machine goes through as it reads the input string, that will be n plus 1, and hence p plus 1. Right? So this sequence of p plus 1 states must have a repetition, because p plus 1 or n plus 1, there are only n different states in your big queue. There are only little n states in your machine, M, your DFA. Okay? So if you have a sequence of p or n, little n plus 1 states, one of them at least must be a repeat.